Deadlock avoidance algorithm is one more method to handle the deadlocks. Okay, so in this deadlock avoidance algorithm, there is first the processes has to inform the operating system about their maximum number of resources that will be used while in its execution. Okay, in its lifetime of execution, how suppose that how many printers are you required, how many scanners are required, okay, how many files are required, is there any tape drives or hard disk drives or dvd drives are required, how many numbers are required, even we have to give with the numbers also. Okay, so this deadlock avoidance algorithm is suitable for the resources with multiple instances. Okay, with multiple instances, that means each process first informs the operating system that maximum of these many resources I need, that is a b c, I need these three resources. So I need three resources of a, two resources of b, four resources of c to be required to finish that particular process execution. Okay, so based on this information, the operating system decides whether the request will be granted to the particular process or immediately granted to particular process, or the process has wait for some particular time. Okay, so there are several other information that is needed by operating system, that is currently how many resources are available, currently how many resources are available, currently how many resources are allocated to each process. Okay, so if we allocate this process, okay, so current p0, if we allocate the requested amount of processes, whether the system will go to deadlock or not. Okay, based on all these factors and all this information, it will decide that whether the request will be granted immediately or it will the process has to wait for some time. Okay, so this particular algorithm makes sure that the system will not go to a circular wait state. Okay, that means so it will not go to circular wait state, because circular wait will leads to deadlock. Okay, right. So the resource allocation state is defined by the following information. What is that? Number of available resources. Okay, so first system will maintain total number of resources. System will maintain total number of resources of each type. Suppose there are three resource types a b c. Okay, if there are 10 resources of a, 7 resources of b, 5 instances of c is there, that means assume that there are 10 printers and 5 scanners and sorry 7 scanners and 5 shared files are assumed like this one. Okay, so these many are there, and out of these how many printers are allocated, how many uh, are available right now. Assume that number of allocated printers are 7 and available is 3. Okay, so available is 3 and allocated is 7. Similarly scanners, 2 scanners are allocated and how many are left, 5 are left. So these, okay, so 2 are available, 5 are allocated. So this information is also called as resource allocation state. Then the maximum demands of each process, these three things we need to we need the operating system will take it, okay, as consideration before allocating granting that particular request. Okay, so this deadlock avoidance algorithm uses a algorithm called Banker's algorithm. Okay, uses an algorithm called Banker's algorithm. So this Banker's algorithm will implement system with multiple instance of each resource type. So this algorithm is divided into two parts. First one, safety algorithm. Second one, resource request algorithm. Okay, so safety algorithm decides whether system is in safe state or deadlock state. Okay, once we find that system is in safe state, then whatever the request is asked, request is requested by process px. Okay, we'll check whether this particular request, okay, is granted or not, or within the limits that is asked by the process or not. Okay, right. So if the system is in safe state, we'll try to allocate the resources. If the system is in not safe state, then the process has to wait for some time. Okay, so let's see safe state. Okay, so before going to safe state and resource request algorithm, let's see what are the data structures that are used here. Okay, so let us take this particular example, and the data structure. First one, how many number of processes are there? So n number of processes. Here the value of n equal to 1, 2, 3, 4, 5. Total number of processes are 5. And how many number of resources are there? 3 resources. 1, 2, 3. A, B, C. So total number of resources are 3. Okay. Now how many resources are available at the current time? Okay. So how many resources are available? We'll consider it as a vector. Okay. So that is available of m, that is available of 3 we can take. Okay, so available of m, that is 3, 3, 2. Okay, then there are three matrices that we are going to use, that is max matrix, allocation matrix, need matrix. Okay, so max of n cross m, that is 5 by 3, allocation of 5 by 3, need of 5 by 3. Okay, so each row in the max will define how many number of maximum instances required by each resource type. That means at the end this particular execution, the process execution completed, P0 requires 7A and 5B and 3C resources. 3C resources. Similarly, P1 requires 3A resources, 2B resources, 2C resources. Okay, that is all of them has to be uh, specified before start of this particular execution. Then allocation matrix. That means at current, these are the resources that are already allocated to each process. That means P1 has one resource B and it does not have A and C. But how many needed? 7A is needed and 3C is needed. Out of 5, only one is allocated here. Out of 5, only one is allocated, one B resource is allocated. Okay. Similarly, for P1, it needs 3 resources, but currently it gets 2. Okay, it needs 2 resources of B and 2 resources of C. Currently B and C is not allocated, so it needs 1 A resource and 2 B resources and 2 C resources still. Okay, so that is allocation. When it comes to need matrix, if we subtract max matrix minus allocation matrix, we'll get need matrix. That means still each process, how many resources are needed will be decided by need matrix. So what is the formula for finding need matrix? Need matrix equal to max matrix minus allocation matrix. Okay, right? So here it is easy that, see, available of max of ij comma k, that means suppose this one, what is meaning of this one, max of ij comma k, that is p0 requires 5 instances of b. Okay, right? Similarly, if allocation of ij equal to 1, that means p0 requires 1 b allocated 1 b instance. Okay, 1 b resource instance. Okay, right? So these are the data structures that we are using. So initially we'll have max matrix, we'll have allocation matrix, we'll have available matrix. Apart from this one, there is something called total matrix. Okay, total of how many resources? 3 resources. Okay, total of m. Okay, so here we need to find the total. How to find the total? Okay, so number of allocated resources of A, 2, 3, 2, that is 7. Okay, 7 plus 3, total 10. Okay, 10. So 1, 1, 2 plus 3, 5. 2, 1, 2, that is 5 plus 2, 7. Okay, so there is a total matrix initially, followed by max matrix, allocation and available. These are the data structures that will be used. We need to find the need matrix by subtracting max minus allocation matrix. Now let's come to safety algorithm. Safety algorithm is of 4 steps. This works in 4 steps. The first step is initialization part. Okay, in the initialization part, see, we are not actually allocating the resources. We are checking that whether there may be a deadlock occur or not. Okay, that's why we are not disturbing available matrix. Okay, that's a original matrix that we'll keep it there, and we'll store that particular available matrix into a available vector into a temporary vector called work. Okay, then we'll take one more a vector, that is finish of I, which represents that how many processes has finished its execution. Okay, that means how many process has getting all the resources that is needed and finish its execution. So this I am taking finish vector. Okay, finish vector is of 0 1 2 3 5. It is the size of uh, processes. Okay, so how initially all the process are not finished, so all of them are false. Okay, all of them are false. So work equal to available means initially how many are available here? 332. So that 332 will be copied to work. Okay, then we'll find the first process, which is finish of I equal to false, and we'll check whether the work that is initially available, okay, currently available, is less than or equal to need of process or not, process P or not. If it is these two, this condition is satisfied, then we'll go to step 3. Okay, so in step 3 we try to add work plus allocation of I, so that the work will be increased. Okay, then we'll write finish of I equal to true. Okay, finish of I equal to true. Then we'll go to again step 2. We'll do it this one for next process, that is Pi is completed, then we'll continue it for Pj, Pk, and so on. So this will be a continuous process, so this will be used in a loop. It will be a continuous process until and unless all the processes has finished its execution. So if all the process has finished its execution, we can say that finish of I equal to true. Okay, if all the process will have finish of I equal to true, the system is in safe state. If any one of the process, if the finish of I equal to false, then we can decide that the system is not in the safe state. We are not going to next step, next part of the algorithm. If the finish of I equal to true for all these things, we'll get a safe sequence. Okay, so with that particular safe sequence, we'll move on to next algorithm called resource request algorithm. In the resource request algorithm, we need to check again two conditions. First one, if request of I less than or equal to need of I or not. Okay, then we'll move on to request of I is less than or equal to available or not. Okay, so if the requested resources is not, it is, if this condition fails means no, the requested resources number of instances is less than available or not. If it is fails, then we don't have the resources that can grant this particular resource. If we have the resources, that means it is also satisfied, it is also satisfied, then we'll implement these three formulas, that is available is equals to available minus request of I, allocation equal to allocation plus request of I, need of I is equals to need of I minus request of I. Then we'll get a state again. Okay, for this particular state we'll try to find whether the new state is safe or not. If it is safe, then we'll allocate the resources. If it is not safe, then we'll go to the previous state. We'll reinstall or restore the previous state. Okay, so we'll see one example in the next video, so that it will be clear what is this particular steps. It will be clear if you take one example, okay, with this particular values.